Sounds like it. Okay, thank you everyone, and thank you for the wonderful talks we've had so far. I'm Aleks Koziell-Pipe, a PhD student at the University of Oxford, and today I'm going to talk to you from almost a pure mathematics perspective on hybrid classical quantum machine learning algorithms with string diagrams. So to set the scene, we're in the NISQ era of quantum computing, where quantum computers aren't yet sufficiently large nor sufficiently fault tolerant for practical uses of things like Shor and Grover's algorithm. And hybrid quantum classical algorithms, where there's an interplay between classical and quantum computations, offer a pragmatic solution to this. In fact, quantum machine learning algorithms such as the variational quantum eigensolver are hybrid algorithms. And in our work, we formalize these hybrid algorithms in terms of symmetric monoidal categories. What this gives us is some really nice but completely rigorous formal mathematical diagrams to describe these algorithms. The formalization gives us a rigorous mathematical framework in which to describe these algorithms. Furthermore, we find that the maths captures some important characteristics of these quantum classical algorithms. And we can also integrate them with ZX diagrams, which allows us to do a sort of in-place quantum circuit optimization, where we can optimize these hybrid algorithms without having to separate out the quantum and classical parts. So just for anyone who's not familiar, the ZX calculus is a graphical language for reasoning about quantum computations and circuits. Applications include quantum circuit optimization, quantum error correction, and measurement-based quantum computing, just to name a few. And these diagrams are generated by Z spiders, the green ones you see on top, and X spiders, the red ones you see on the bottom. And they correspond to the quantum processes shown. We also have some syntactic sugar for the Hadamard gate, which we can express in terms of these Z and X spiders, as you can see here. Familiar quantum gates and quantum states are all expressible in terms of the ZX calculus. And we also get rewrite rules, allowing us to transform one ZX diagram into another. This is where applications like quantum circuit optimization are useful, because we can take one ZX diagram, representing a quantum circuit, and rewrite it into a smaller diagram, which is more computationally efficient. Now I'll move on to category theory. So category theory studies mathematical structures and the relationships between them. It's a high-level approach, and it focuses on the general patterns of how these mathematical universes connect and interact. And in our context, when we apply it to hybrid algorithms, we're interested in the mathematical universe of quantum systems and the mathematical universe of classical systems and how they interact. We'll see that actually, I've drawn in terms of diagrams, we get interesting things like quantum measurements producing a single classical value corresponding to the measurement probability. So what is a category? At its bare bones, a category is made up of objects and morphisms. These objects we can think of as systems, and we draw as wires. These morphisms we can think of as processes, and we draw as boxes. These systems can be a number of things. They could, for example, be vectors of real numbers, and these processes could be something like arithmetic operations, computing the loss function from a neural network, or if our systems are pairs of complex numbers corresponding to a single qubit system, our morphisms could be quantum circuits, like the one you see here. So we have a way of defining a classical universe and a quantum universe, but we need a way of going between them. This is done by a functor. So a functor is a structure-preserving map between two categories, or two mathematical universes. For example, we could take one that turns the ZX diagram into the complex matrix or vector that it represents. The fact that the functor is structure-preserving means that if I break this diagram down into small pieces, apply the functor to each piece, and then multiply together the resulting vectors and matrices, I get the same thing had I just applied the functor to the entire diagram. In terms of string diagrams, we can actually draw the application of a functor as a box. What this means is that I'm applying the functor to this red spider, and on the outside of the box, we have our classical category. This allows us to show that we're mapping this red spider into our classical category and nest it inside an entire diagram for classical systems. For anyone more familiar with category theory, our quantum system is actually the category of completely positive superoperators on two-dimensional Hilbert spaces. This category is compact closed, which intuitively means that it captures things we want in quantum information, like no cloning and no deleting. For the classical system, we define the Cartesian category of smooth maps between Euclidean spaces. The Cartesian fact means that we can copy and delete information freely, as we would expect in classical systems. And the fact that we're using smooth maps allows us for differentiating things which we want in our machine learning applications. So we've got two things to do. We've got to go from this no cloning, no deleting kind of universe to a freely copying, free deleting kind of universe. And we also want to be able to differentiate things. So we do this by going through an intermediate step. First, we define a category of real matrices, and we map from our real matrices, our quantum system, to these real matrices, using a functor which I've shown the definition of here. Intuitively, and as some concrete examples, it expresses these quantum superoperations in terms of a Pauli basis. So what we get is that our Z state gets mapped to this vector, our X state gets mapped to this vector, Z and X rotations get mapped to these matrices, Hadamard gates get mapped to this matrix, and a C0 gate gets mapped to this matrix here. So we've now been able to go from our complex amplitudes to our real matrices. The next step is going from real matrices to smooth maps. Now, because matrices represent linear maps which are smooth, that part is fairly straightforward. However, there's a subtle difference between compact closed and Cartesian in category theory. So when we define a functor going from these matrices to smooth maps, and then compose it with our previous functor, we get a functor from our quantum system to our classical machine learning system that has a special property which we call lax monoidal. In terms of diagrams, what this means is that if we apply a functor to a system with our functor box, we can have multiple wires entering the box being preserved as multiple wires. However, when multiple wires leave the box, they always get bundled into a single wire. Looking at our hybrid algorithms, what that means is that when we encode classical data onto the quantum system, the wires are preserved. However, even when no wires are leaving the box, we get a single wire out. This is quite nice for measurement because it means that if we have a diagram here which corresponds to a measurement, we still get a single wire out, which feeds a classical measurement probability into our from our quantum system. To show this concretely, I applied this framework to a quantum machine learning paper from 2018 where a parameterized quantum circuit is used for MNIST classification. The diagram here I've shown is slightly simplified for clarity. So at the moment, this diagram is just purely a quantum system. However, what we want to do is clearly delineate which parts of this are quantum, which parts of these are classical, and actually include some diagrammatic representation of things like computing expectation values and having a loss function. So the first thing we do is we put a functor box around our diagram. We then do some classical post-processing, where we compute an expectation value, we compute a loss function, and then we pull out the parts of our quantum system that actually correspond to classical data being encoded onto the quantum system, and parameters that we're going to optimize with the classical optimizer. So what we're left with is a fully formal mathematical description of this hybrid algorithm. So in summary, we took a diagram like this, where we have the interplay between different quantum and classical computations, feeding information between each other, and provided a rigorous mathematical description of this. This description is also amenable to ZX-based optimization methods. What we want to do in further directions is there is in fact some category theoretic work as applied to classical machine learning, which allows you to express reverse derivatives and gradients and parameter updates. So we'd like to extend our work with this kind of formalism. What that means, though, is that because we're computing the gradients of quantum circuits, we have to use techniques like gradient recipes in order to calculate these gradients. It turns out that there's actually some existing work using an extension of the ZX calculus called ZXW that allows you to express these gradients as a diagram. So with these two future directions, we aim to try and formalize the entire hybrid quantum machine learning algorithm with our forward pass and backward pass in terms of all these diagrams. Another fun sort of side project would be to start implementing this in software where your high-level API is all in terms of these boxes and wires and these functor boxes and trying to wire things together. Okay, well that's it. So thank you very much.
Thank you for the talk. Questions? Okay.
I've got a slightly provocative question. So we just heard, I mean, so quantum, as you started by saying that in the current era of quantum computing, we're still sort of not there yet with big enough systems. And yet these ML methods are, you know, they deal with enormous, I mean, you know, that, you know, billion parameter systems that operate on petabytes of data. So are these, this field of combining ML with quantum, is it more than just taking two great buzzwords and making them coexist, or is there something real in this, or is it something that's going to be real in the future?
Well, I think that question is definitely beyond my level of expertise now, having not even done my thesis. However, one of the things I think is nice about this framework is that although I did it in terms of trying to, with the intention of looking at smooth maps, derivatives, that sort of thing, one thing I found actually while doing this is that it seems like one of the, although this hybrid paradigm we talk of as like, you know, while we wait for the bigger quantum computers to come along, it seems to me that there might be a situation in which we actually, and actually I think Bettina's talk earlier speaks to this, and we're actually interested in having CPUs, GPUs, and QPUs, just all our different processing units working alongside each other for the tasks that they're good at. In terms of the parameters and having lots of parameters in the machine learning model, I suppose what this also allows you to do, which I haven't illustrated in diagrams, is that these functor boxes actually have fusion rules. So if we then try to describe something slightly bigger like this, where you have lots of quantum systems and classical systems all over the place, you could actually have billions of parameters all pulled out, feeding into different parts of the algorithms that are quantum, and effectively have some interplay between these sorts of things. In terms of scalability, we'll have to see how things go with the future developments. Thank you.
So just a comment and a point. So the comment is DARPA has a project going on at the moment on building the benchmarks we should be working on the next 10 years. And the first thing they did was to get rid of quantum machine learning, because that's just not for the next 10 years. Anyway, on this thing with building the gradients, I very much recommend Xiaodi Wu's paper from PLDI 2020. It shows how to build the gradient circuit essentially by taking pieces up of the circuit that you want to differentiate. It's very neat. And so yeah, I've been teaching that paper in my class many times and it's very neat.
I'll grab that reference from you. Thank you.
Very nice talk. Thanks. One question. Now, especially with quantum error correction, we start to have these sort of like feedback loops and mid-circuit measurements. Would they be amenable to be cast in this formalism, like, is that still everything is a quantum, or some parts are like sort of like classical subroutines? And the other question is, it's just a naive maybe comment from my point of view. When you were sort of like expanding into bigger matrices, those operations, and also the fact that you mentioned super operators, it reminded me of the treatment of certain kind of compact noisy operations, where you expand your matrix into, thanks to a super operator, into a bigger object. So I don't know if does noise, can noise be represented, simulated here, or maybe it's beyond this because it's more a tool for compilation.
So I think at the moment there's no noise model. I think that's the limitation of the categories I'm using, which are the smooth is the classical category is deterministic. I'm sure there's work on using more probabilistic categories and things like that to try and simulate noise. In term addressing the previous point, there is, in terms of intermediate measurements, there is work in using the ZX calculus for expressing intermediate measurements. They do that by actually by placing sort of parameters in the ZX diagram. I suppose what you could have is you could have I would expect that you can have measurements feeding out of your boxes and feeding into other boxes. In terms of measurements in the actual diagram, I haven't looked at that enough to know whether you'd be able to have kind of measurements within the same diagram feeding out of the box and coming back in somewhere.
Thanks.
Yeah, I actually have another comment to the quantum machine learning question. There's this theorem called Aronson-Ambainis conjecture, which basically says that quantum algorithms in general work better on problems where you have only a tiny amount of data, but a lot of structure. So Shor's algorithm obviously is a very nice example of that. And as it turns out, actually the same also applies to quantum machine learning. There has been a paper where they made a quantum machine learning model learn a discrete logarithm function, which also seems to be classically hard. So like if you want a classical neural network to learn discrete logarithm, this also seems to be exponentially expensive. For quantum machine learning, that seems to work.
Well, is there any other question? So about the quantum machine learning, just take your comment. So the model you are modeling here is quantum neural network, to say. So this is a hybrid. You have the quantum part, and the optimization is completely classical, okay? But there are purely quantum machine learning model, okay, which are based on the implementation of a quantum kernel. Those methods are much more promising because they are completely quantum, okay? So they, from that kind of model, one of these is exactly what he was saying, is based on quantum algorithms that are exponentially faster, okay? And therefore not implementable on this NISC, but they require a fault-tolerant quantum computer, but they are provable. I mean, their advantage is provable, okay? So, it would be nice to see how these kernel models can be, you know,
yeah, I'm familiar with this work, I think. It's by Maria Schuld is one of the authors with the quantum support vector machines.
Exactly.
That's actually what's got me started thinking about this, because they do a lot on encoding data on quantum computers.
Yeah.
So originally this problem came about because I was thinking about, okay, well, we draw a quantum circuit and then we put all these numbers on it, but actually those numbers come from classical data that we've then put on the quantum computer. So that's almost exactly what you see here. In fact, what I was doing is this is basis embedding, where you're you've got a binary, those x1, x2, x3, x4, that's a binary string, and then you're trying to turn it into a qubit system. Yeah.
Okay, I can introduce the final talk. Thank you again.